Okay, the next topic is resistance to airflow. So if the bronchiole dilates, becomes larger, bronchodilation. If the bronchiole constricts, bronchoconstriction. If the bronchiole dilates, then there's going to be more space, so more air goes in. If the bronchiole constricts, less air goes in, so that determines obviously the resistance to airflow. There's going to be more resistance if you have bronchoconstriction. Next one, pulmonary compliance. Pulmonary compliance got to do with the ability of the lung to expand. If you have a scar in the lung, like for example, for somebody that has tuberculosis, then the lung will not be able to expand the way it's supposed to. Therefore, you're going to have less air going into your lungs. So let's keep going down. Next topic is alveolar ventilation. That's basically the amount of air that goes in and out your lungs, inhaling and exhaling basically. How do you measure that? You measure it with a device called a spirometer, right here, spirometer. So in the process of measuring these values, the amount that goes in and out is spirometry. Let's keep scrolling down. And there's multiple different types of volumes and capacities. So which ones are the volumes and the capacities that we have in our lungs? You have in here the names. Right here, you have an spirometer. You can see the person blows in this table. You have the different volumes, the values, and the definition. You also have the capacities and the definition for each capacity. There's variations in respiratory rhythm, obviously, because we are not constantly just resting. So we are exercising, we are laughing. So because of this, there's going to be changes in ventilation. The next topic in this chapter is gas exchange and transport. So the first thing that we have is composition of air. As you can understand, the air is not pure oxygen, right? So then right here you have a table where you can see the composition of the air. So most of the air that we have in the environment is nitrogen. 20% is oxygen approximately. Little amounts of water and carbon dioxide. Right here you have inspired air, the air in the environment, but this is the air that you have in your alveoli. Okay, next thing we have right here is gas exchange. We need to exchange the gases between the alveoli and the capillary. If we keep scrolling down, pressure gradients of gases, we said that we have different gases. So if the pressure on these gases change, that's going to change also the gas exchange. You have a figure in here. This is in your tissues. So you have more carbon dioxide in your tissues going into your blood. And obviously you're going to have more oxygen from your blood going into your tissues. If we keep scrolling down, right here you have another table where it says that the more pressure you have, the more unloading of oxygen. Okay, so then right here you can see this is normal. This one is a high altitudes, for example, air 3000 meters. At high altitudes, you have less air, therefore less oxygen, and there's a slower diffusion of oxygen. So if we keep scrolling down, what else affects that? Solubility of the gases. Some gases are more soluble than others. Like for example, carbon dioxide is more soluble than oxygen, but there's more pressure of oxygen, so at the end the exchange is more or less the same. Membrane thickness, obviously if the membrane is thicker, like in this case, the gas exchange is going to be slower when compared to this one. Keep scrolling down. Emphysema, in this case, you lose alveoli. You lose that tissue. So then obviously that's going to affect that membrane area, right? You lose the alveoli, then you're going to have less membrane area. Ventilation, perfusion, gas exchange. In order for that to happen, you need blood and you need oxygen. What happens if for whatever reason you don't have enough air because, that part of the lungs is lost because there was an infection, etc., etc. So because of that, there's going to be an arrangement in the blood flow to areas where have good amount of oxygen at the level of the alveoli. So there can be a good perfusion between the air in the alveoli and the air in the red blood cell. In other words, you will be able to perform the gas exchange. Let's keep scrolling down. Gas transport. Oxygen gets transported with a hemoglobin. If you have attached to the hemoglobin, it's oxyhemoglobin. If not attached to the hemoglobin, it's deoxyhemoglobin. Each molecule of hemoglobin can transport up to 4 oxygens. The moment that one oxygen gets attached to the hemoglobin, it stimulates the attachment of the other one and the other one and the other one, and this saturates the hemoglobin faster and faster. There's one curve that you can use in order to understand that, and that curve is here, the oxygen dissociation curve, right here. You can see the percentage of oxygen saturation of hemoglobin depends on the partial pressure of oxygen. Let's take a look at these 4 squares. And let's assume that the red line goes through here. So when the partial pressure is 20, the percentage of saturation is 20. Let's jump to more. So when it's 40, it should be 40, right? Double, but it's not. It's actually all the way up to pretty much 80. Why? Because this part shows you that when it attaches one hemoglobin, the attachment of the other oxygens to the hemoglobin is faster and faster and faster. Therefore, there's a steep increase in the amount of oxygen saturation. So let's keep scrolling down. And the next topic is how the carbon dioxide are going to be transported. Carbon dioxide is transported mixed with water with this reaction. It's going to be bicarbonate. And number one, it gets transported as bicarbonate. Number two, it gets transported attached to the hemoglobin. 90% is transported at bicarbonate, 5% is attached to the hemoglobin, and the 5% remaining is going to be free as dissolved gas in the blood. Right here, systemic gas exchange, the tissue and the blood. Since this is a tissue, we need to give oxygen to the tissue, and the tissue must provide the carbon dioxide back into the red blood cell. Why do we have 3 arrows? Because we know that the carbon dioxide gets transported in 3 different ways. Carbon dioxide gets dissolved gas in the blood. Another percentage is attached to the hemoglobin, but the biggest percentage gets transformed into bicarbonate right here through this chemical reaction. Carbonic anhydrase is the enzyme that is going to allow you to have this type of chemical reaction. One very important part in here is that this bicarbonate can be used as a buffer in order to control pH. How do you remove this bicarbonate from your red blood cell? Because you can exchange it with chloride, and this is called the chloride shift. This is bicarbonate. There's one hydrogen in here. This hydrogen attaches to the hemoglobin, and when it attaches to the hemoglobin, it allows the hemoglobin to disassociate from the oxygen. Therefore, the oxygen is free now. It can be released into the tissues. Most of the oxygen is transported attached to the hemoglobin, but some of the oxygen also goes dissolved in the blood, as you can see right here. But it's just a tiny amount.